Okay, so Assalamu alaikum everyone. My name is Samra Mirza. I'm a second year medical student, and today we will be making glucose, or this process is also known as gluconeogenesis. Um, so some ground rules to set, obviously. If you have any questions or if you need to stop me for those attending, you can stop me at any time. You can unmute your mic, you can write in the chat, whatever is comfortable for you. And for those who are hopefully watching the recording, I hope this benefits you. So today we will be making glucose, and this is essentially making glucose from a non-carbohydrate source, unlike other processes, like unlike glycogenolysis, which is breaking down glycogen into glucose. You are making glucose from a new source, something different. So to begin, these are our objectives for today's PAL session. We are going to go over the sources of glucose in the body. We're going to go over the process of gluconeogenesis. We're going to discuss the regulation of it. And then we're going to move on to a brief comparison between gluconeogenesis and glycolysis. Then we're going to go over the precursors of gluconeogenesis, essentially what molecules are used. And then we are going to go and discuss Cori cycle and glucose alanine cycle. Now, these objectives are from your lecture, by the way, so I would suggest that you try to make sure that you know all of these because this is what the doctor wants from you. So to start, our sources of glucose in general in our body, right? We have three main sources that you can see on the graph here. We have exogenous, and this essentially just means your diet, right? This is things that you are getting from your diet. So this includes any sort of meal, especially carbohydrate heavy meals. They have a lot of glucose, but these can only last you up to 4 hours. And then your body starts using its glycogen sources and it's going to start breaking them down. So from hours 4 to like 12, you are intensively using your glycogen. And then you can see that the glycogen store starts going down. And so we start moving on to a new process called gluconeogenesis, which is building glucose from non-carbohydrate sources, as I've mentioned. And this, you can see that it starts to take over the glycogen process, or the glycolysis, and it starts to increase after hour 16, and it continues up to like 40 days, for example, in the cases of starvation. Now, glycogen can last you your overnight fast, and that essentially just means, when you're sleeping and you're not eating during that time, glycogen it can last you up till that time. And then after that, you're probably going to start relying on gluconeogenesis. So at some point when you're fasting, your body is going to move away from its glycogen stores because they're getting depleted, and it's going to move into gluconeogenesis. And this can last from hour 16 to say 48, and like so on and so forth for as long as you need it. And glycogen, in worst case scenarios, as you can see, it can go up to day 2, but preferably you're going to move to gluconeogenesis. Next, who needs glucose, right? So technically everything needs glucose, but some things can rely on other what's called sources of energy. Some can rely on fatty acids and ketone bodies, but some structures need glucose specifically, right? So the brain relies heavily on glucose, and only in the worst case scenarios, it's going to rely on ketone bodies, which are formed from, well, technically fats, and this is a process you're going to learn next year. RBCs, well, as you can see, they're kind of empty in the head, right? They don't have anything. They only have hemoglobin, and they lost everything to get that hemoglobin. So they don't have mitochondria, for example, for like further usage and further production of ATP. They only have like simple pathways that they can use for glucose breakdown. So they are mostly doing glycolysis, which is a very, very simple process, and it can generate like a few amount of ATP, but it needs glucose and it cannot rely on anything else. So RBCs need glucose. For other stuff, you have the kidneys and their medulla, you have your exercising muscles, you have your corneas, and your testes, which also rely on glucose, but obviously they can also rely on other sources when needed. Like muscles can rely on creatinine. Anyway, moving on, where does gluconeogenesis occur, right? So the location of gluconeogenesis is dependent on the presence of certain enzymes. And these enzymes are not present everywhere. That's why like muscles, for example, cannot have gluconeogenesis, and we'll get into this in a bit. But the main organs where gluconeogenesis is taking place is in the liver, and that's 90%, and then 10% in the kidneys. And that's about it. And I think it's better to just know that majority of gluconeogenesis takes place in the liver. Then we have to, before we go into gluconeogenesis, we have to revise glycolysis, because glycolysis is the production of ATP by breaking down glucose, and you're getting into the final product of pyruvate. So it's glucose to pyruvate. But gluconeogenesis is a reversal of most of it, with what's it called? Some stages that need to be bypassed because they have what's known as an irreversible reaction. So technically, this is the entire process that you have for glycolysis, and you can see that those with the green arrows, these are reversible reactions, so you don't need to worry about them, they're just occurring. But these with the red arrows, they're only showing one direction, these are irreversible reactions. And these are very, very important because these have to be bypassed, and these need a detour for us to now create glucose. And their enzymes are important because we're making a comparison. So from glucose to glucose 6-phosphate, we use glucokinase and hexokinase, the difference being glucokinase is in the liver and hexokinase is everywhere else. Then, a bunch of intermediates later, we move on to fructose 1,6-bisphosphate being produced from phosphofructokinase 1, which is this one. And a good way to remember this enzyme is just know that the 1 is giving the position of where the next phosphate group is being added, because that's what a kinase does, it just adds a phosphate group. And then more intermediates pass, irreversible reactions taking place. Then you have pyruvate kinase, which essentially phosphorylates phosphenol pyruvate, which is PEP. And that it gives you pyruvate. So these are the reactions of glycolysis. Now, how do we bypass these? How do we get through them? Well, we take a detour. It's a very fun picture, if you ask me. And so we are going to work in a kitchen environment, right? Let's imagine this. And, when you're baking, you try to separate your ingredients. You're going to have wet ingredients and dry ingredients. Don't ask me which bowl is which because I really don't know. But just pretend one bowl is representing the mitochondria and one is representing the cytosol. So this is our environment, but we also need help. We can't just do this alone. So we have some family members who are going to help us out. And I promise I'm not playing around. But okay, I'm playing around a little, but this is also just to help you memorize these better, right? So you have your mother, and your mother is very sweet. She's very sweet. She's so sweet. She's just like glucose, sorry. So that's your mother. She is representing the enzyme glucose 6-phosphatase. Then you have your father. There's not much for the father, but there's an F and there's an R. So remember this is fructose 1,6-bisphosphatase. And then you have your brother who loves Pepsi and carbs, and he's 10 years old, okay? And he is representing Pepsi K, the enzyme, and he's representing pyruvate carboxylase, both of them. Now, these are the enzymes that are directly counteracting the actions of the enzymes that we were using in glycolysis. So we'll start, this is the original direction that we had for glycolysis, so we're going to go from bottom to top now for gluconeogenesis. So pyruvate kinase is going to be counteracted with the actions of this child, which is Pepsi K and pyruvate carboxylase, and then your father and then your mother. These are your family members who are helping you out, but you also need to be kept in check or, regulated. So your grandma's here for that, and this is Granny Lucy, GLUC, glucagon. Very, very, obvious, clearly. So she decides everything, and she has a sweet tooth. That means essentially that she's going to be increasing your blood sugar levels. And she loves her grandchildren. Okay, then you have some more regulators. You have the father of the father, technically your grandfather, but this is a really important father. This is fructose 2,6-bisphosphate. They're very important even in the glycolysis lecture, and they have a role here as well. You have your really cool aunt or Aunt Cool, and she is the one giving her nephew, aka Pepsi K and pyruvate carboxylase, the permission to cook, right? And her name is essentially just mnemonic to remember acetyl-CoA, also very important. And then you have your little sister. She loves her ABCs, just ATP, biotin, CO2, and she plays with her brother very often, right? So I don't know about you guys, but ABCs were always just so very hard for me. So I think we just, we need to revise them, So what are our ABCs? we have ADP, we have biotin, and we have CO2. So as we know, glycolysis is a reaction, that is giving us ATP in the end by breaking down glucose. So this is somewhat of a catabolic reaction. And going back up to produce glucose is going to be an anabolic reaction, and it's going to require energy. And you're going to get energy from ATP. So this is the ATP that we have. And this comes from beta oxidation. And so this reaction of beta oxidation is going to break down fatty acids, and you're going to learn more about beta oxidation next year in MOL 2 or next semester. And this gives you ATP, and it also gives you acetyl-CoA. So it's essentially giving to on cool. And this is important to know because we'll come back to this in a bit. And then biotin, this is an activator of all carboxylases. And what's it called? Especially in this case, our carboxylase is pyruvate carboxylase. Sorry for a second. Yeah, sorry. Anyway, you have biotin, which is an activator of all carboxylases. And our carboxylase in this case is pyruvate carboxylase, which is our little brother. And it hates raw egg whites. They're very, very stinky, and we'll come back to this as well a bit later. And then we have CO2. So carboxylase enzymes essentially are adding a CO2 group to a molecule. So obviously you need a CO2 to do that. So that's what this is. So I hope the ABCs are clear. Does anyone have any questions up till now? Is there anyone here actually? Okay, does anyone have any questions up till now? Okay, crystal clear. Okay. Okay, thank you. Again, if you have any questions, you can obviously unmute, or you can write in the chat, whatever you need. So thank you. So now we're going to move from bottom to top, right? So we're starting with reaction 10, because the irreversible reactions were 1, 3, and 10. So we're going to start with reaction 10. So this one takes place in the mitochondria first, right? So you have your little brother who is 10 years old. So, use that information to remember this is going to be involved in reaction 10. And you have your little sister who just loves her ABCs. And you have Aunt Cool, who just had to be there for her nephew, meaning that she was an obligate activator of the enzymes, specifically pyruvate carboxylase here. So you take pyruvate, you put it in the bowl. You also add pyruvate carboxylase, and you add your ABCs because these are all involved with the pyruvate carboxylase enzyme. As we know, we need ATP, we need biotin, and we need CO2. So you're adding that. So all these 3 people are involved, right? Then we move on to this is, as you know, first step, part 1. Then we have a part 2. Well, technically, before we have the part 2, we actually have a little intro session, yeah. So Aunt Cool, right? She's so cool. She is not only going to encourage her nephew, her pyruvate carboxylase, she's also going to be blocking PDH, which is an enzyme that is used in glycolysis. So again, we don't want the steps of glycolysis to take place. So we are coming to blocking the pathways that are occurring for glycolysis. So we're going to block PDH. And so this is also done by, you can obviously see high acetyl-CoA blocks PDH. And how is acetyl-CoA coming? Again, it's coming from the breakdown of fats, right? You're breaking down fats, you're having beta oxidation, fatty acids, and you're also getting acetyl-CoA produced. So that's what this is. And it's supporting pyruvate carboxylase. Now we come to part 2. So now this reaction of pyruvate carboxylase and pyruvate produced oxaloacetate. So essentially to the molecule of pyruvate, you added a CO2 group. So you move from 3 carbons to a 4-carbon molecule. That's what the oxaloacetate is. And you can see a little bus here. So remember that bus, this, shuttle, I don't know. I don't really know the difference, but you're adding it to another bowl. So say you're mixing one of the wet or dry into the other one, and you're moving it to your cytosol. And to this, you're adding another enzyme called PepCK. And you can notice that we have the 10-year-old here again, and you have Granny Lucy, which is glucagon. And glucagon essentially is an activator of PepCK, and it increases the expression of PepCK. So you're adding those molecules here into the cytosol, and you are getting PEP, phosphophenol pyruvate. And that's about it for this 10-year-old, and they're leaving. So, you can say bye to him. And this is, again, a summary of what we just did. So we know this is part 1 is done in the mitochondria, and the other is done in the cytosol. Sorry for the typo. And then this reaction is using ATP, and it's also using CO2, as we know. Biotin, now we know, is a cofactor that is used for this enzyme. So a cofactor is something that is needed for the activity of the enzyme to take place. You will also learn this in MOL 2. Acetyl-CoA is an obligate activator of this enzyme. Now, the oxaloacetate produced in the mitochondria has to be transported to the cytosol, and that is done via a malate shuttle. So that's what this bus is. That is our malate shuttle. All right. Sorry. And then after it moves into the cytosol, you have Pepsi K acting on it, and it is using GTP. And GTP is coming from the Krebs cycle, and it's coming from the conversion of succinyl-CoA and succinate. Right. So this is very important, and you need to know this. So it's using GTP, and it's again producing the EP. And glucagon, granulosi, is increasing this expression. Right. So this is step 10's reversal done. Does anyone have any questions for this part? No questions? I don't see anything in the chat, so okay, I'm going to assume and hope there are no questions. If there are any questions, again, you can obviously write in the chat or unmute. Okay. Oh, checkpoint. Thank you. So, okay, no questions. Lovely. So now we have a checkpoint. This is from a very, very reliable source, which will just not be named, because who cares about naming sources in this place? I'm all about plagiarism anyway. So this is a very reliable source, and you'd have to trust me in how reliable it is. And so the question is, a deficiency in the action of biotin would lead to accumulation in which of the following? Now remember, biotin was used for the reaction of converting pyruvate into oxaloacetate. All right, that's why, just give it a little help. So which options of A, B, C would be increased when biotin is deficient? Would anyone like to answer? A, okay, lovely, yeah, you're correct. Thank you. If no one has any questions regarding this, they are very much correct. It is A, so good job. Okay, so now we are going to move on to the reversal of step 3, which initially was the conversion of fructose 6-phosphate into fructose 1,6-bisphosphate, and now we are reversing this, right? We want to go back to fructose 6-phosphate. Now, this reaction in glycolysis was rate limiting, and it's a very, very important reaction. So this reaction here is also important just because of correlation. So now you have your father, because he was the one involved in this, and he wants to help. But you also have the father of the father, who was fructose 2,6-bisphosphate, who is quite upset here, and they are leaving, and they're leaving for a reason. And you also have this little girl again, and she is giving you ATP, right? So you are adding, what's it called, fructose 1,6-bisphosphatase to the bowl, which contains fructose 1,6-bisphosphate. Remember that something that has A's in it essentially is removing it. So this was an extra phosphate group that we had at position 1. It's now going to be removed via this enzyme, right? That's what this is doing. And okay, the presence of ATP. This is a very important concept that I think is good to know. The presence of ATP is what's allowing this reaction to occur, right? And having ATP means, having high amounts of ATP means there's a lot of energy. If instead of ATP, say that there was high amounts of AMP, which is the dephosphorylated form of ATP, that would mean that there's not enough energy. So that would favor a reaction that would cause the production of ATP rather than a reaction that causes the formation of glucose using ATP. So having high ATP is a very important factor in the formation of glucose, and it's a very important contributor to gluconeogenesis. AMP, on the other hand, favors glycolysis. Yeah. So, That's essentially what I'm saying here. Fructose 2,6-bisphosphate also, yeah, okay. So this really moody father of the father is leaving, and he's leaving because fructose 2,6-bisphosphate is a stimulator for glycolysis. And it's like an on and off switch. If you have fructose 2,6-bisphosphate, glycolysis is going to occur. If you don't have it, you're going to have gluconeogenesis. So it's gone. The supporter of glycolysis is insulin, while the supporter of gluconeogenesis is glucagon, so granulosi. Granulosi versus a gastric grandfather, also known as father of the father. This is the same explanation that I had. It's here written in words. If there's any questions about this, by the way, you can obviously ask. Is this part clear about the ATP and the AMP? Okay, I see a yes. Okay, I see. So I think this is clear. So I'm gonna move on. Obviously, again, if you need me to go back to any slide for the one attending, you can obviously ask me to. And for those watching the recordings, if you have any questions, you can obviously message me at any given time. So now this is again a summary of what we just took. We're seeing that AMP being high favors glycolysis. Fructose 2,6-bisphosphate also favors glycolysis. Having high ATP, meaning you already have ATP and you don't need more ATP to be produced, it's going to not favor glycolysis, it's going to favor gluconeogenesis. Again, because glycolysis is producing ATP and gluconeogenesis is using ATP. If you already have ATP, you don't want to create more. You're going to use it to create glucose. I hope that makes sense, that concept. And citrate is, again, another product that is used in Krebs cycle, and this also generates more ATP. So it's, again, a signal that you already have a lot of ATP. So high citrate is also going to inhibit glycolysis, and it's not mentioned here for favoring gluconeogenesis, just these are, and you need to know these. Then we come on to our final part of gluconeogenesis, which is reaction 1, and it's reversal, right? So here you have your very sweet mother who cannot be anywhere. And again, very sweet means glucose 6-phosphatase. And again, this means reversal of the enzyme hexokinase or glucokinase, which was adding a phosphate group. So you have your glucose 6-phosphate, glucose 6-phosphatase is added to it, and this in the end gives you glucose. Now, your mother can't be everywhere, and this essentially means that this enzyme is not present everywhere, and it's mostly in the liver and the kidneys, and it's not in our muscles. And that's why the muscles have been referred to as being stingy, because although they can do most of the reactions of gluconeogenesis, they can't do this final step, which would remove the phosphate groups from glucose, which would allow it to leave the membranes, right? That's what this is. And then you have some more help. These are substances or hormones and neurotransmitters that are essentially helping for gluconeogenesis. So epinephrine is a molecule that supports gluconeogenesis and glycogen breakdown. And what do these both do? These essentially cause hyperglycemia. So these are increasing your hyperglycemia and they're causing it. Cortisol, another one, and you can see there's a star here. This is very important in a bit. Cortisol is also an activator of gluconeogenesis, and so are thyroid hormones. You're going to take this next semester in endorepro, these two, so all the best for that. And then we have another checkpoint. Which of the following enzymes is used in gluconeogenesis? And so we have glucose phosphatase, pyruvate kinase, and PFK1. So, if you want to answer. I see an A. That's very good. I see a B. Good for you, I guess. Anyway, yeah, it is A, by the way. So thank you for answering. So note that these two reactions are both involved in glycolysis. Pyruvate kinase is converting PEP into pyruvate, and PFK1 is converting fructose 6-phosphate into fructose 1,6-bisphosphate. Another A, yes, good job. And then you have glucose phosphatase, which is involved in reversing reaction 1. This is your very, very sweet mother. So yes, good job. This is again a very trustworthy source. And now we have some precursors. So this diagram I think is really good. This is from your lecture, by the way. So we'll start from here. So essentially you can go by the process of gluconeogenesis from the bottom. So you're going to start from reaction 10. But in some cases, you can join midway in between of reaction 10. So you have pyruvate, right? This is the one we're working with, and it goes into oxaloacetate and then PEP. PEP goes along the other, intermediates that are going by reversible conversion, and then you come to fructose 1,6-bisphosphate and glucose. Alanine can be converted into pyruvate, and we'll come to this when I come to the cycles. Amino acids also give you pyruvate, and this is from their breakdown. You'll also learn about this in MOL 2. Lactate also produces pyruvate. This is going to be in the cycle I'm going to show you next. Then you have odd chain fatty acids. And this is very important to know that this is only odd chains. Even chain fatty acids cannot be supplying gluconeogenesis, and they won't. So odd chain fatty acids, when you break them down, they give you propionyl-CoA. And propionyl-CoA can essentially become oxaloacetate, and then by a series of reactions, and they can contribute. That's one other source other than pyruvate, right? And then you also have amino acids, you have alanine, and you have lactate. And you need to know these sources. Then you also have glycerol. So when we have the triglyceride molecule, you have a glycerol and you have 3 fatty acids, right? This is our triglyceride molecule. So fatty acids, part of them are broken down and they give you ATP, as we mentioned. Some of them, if they're odd chain, can give you propionyl-CoA. And then the glycerol essentially goes through a reaction and it gives you DHAP, which you learn more about this in your glycolysis lecture, I think. And so from here, again, you can follow the rest of the steps and you can go onwards. So now how many sources do we have in total? We have lactate, we have alanine, we have amino acids, we have fatty acids technically from propionyl-CoA, we have glycerol, and we have pyruvate. So these are a total of, let me do my math really quickly. 1, 2, 3, 4, 5, and 6. We have like 6 sources technically, if I know my math, which is not very reliable, but you know. Then pyruvate and its different uses, right? Pyruvate can become acetyl-CoA, and it can then join the Krebs cycle. And you learned about this in the past session, or if not the past session, then you learn about it in your lectures. Pyruvate can also become lactate and through Cori cycle be recycled to give you glucose in gluconeogenesis. It can be used directly in gluconeogenesis, and it can also be converted into alanine and the alanine glucose cycle and also give you glucose again. And these 2 cycles, I'm going to come to them in a bit. And by a bit, I just meant right now. So we'll start from here, okay? Albeit a cycle can start from anywhere, but this is where we're starting from. So in your muscles, you are breaking down glucose, and this is say when you're exercising, and at some point, when the muscle gets tired, it's going to start producing lactate, right? Now, lactate is going to move along in the blood, and it's going to go to the liver for recycling, right? And the liver is going to convert it back into pyruvate, and this pyruvate is now going to be used to form glucose via the gluconeogenesis pathway. And then it's the same thing again and again, and that's just a cycle. So that is Cori cycle for you. So one more time, glucose is being broken down anaerobically at some point in the muscles, and this is going to give you lactate. Lactate is going to move on into the liver, convert it back into pyruvate, and then via gluconeogenesis, it's going to give you glucose, and then it's a cycle. So this is just about the recycling of lactate in the body. Cori cycle and alanine cycle, sometimes they can be asked in the exams, albeit sometimes they can focus on anything else. This is a very memorization-heavy lecture, so it can focus on about anything. Then you have the glucose-alanine cycle. So for this one, start from the muscles. So muscles sometimes can also break down amino acids because, as we know, muscles don't just rely on glucose. They can rely on creatinine, they can rely on fatty acids, and sometimes they can just break down the proteins to give them the energy that they need. So in some cases, you can have amino acids, and when amino acids are broken down, you're going to have an amino group being formed. And this is essentially ammonia as well. And ammonia is a toxic substance, and it has to be either removed from the body, which is through urine, and we're coming to that, or it can be transported, or it can be added to something else and then transported to the liver for further processing. So in this case, pyruvate, the 3-carbon molecule, has an amino group added to it, and this forms alanine. Alanine, which is now a safe molecule as compared to NH3, can be transported in the blood, and it's going to go into the liver. And from this point onwards, now the liver can deaminate it and remove the amino group again to give you urea, and then remove the amino group and then convert it into urea, and then it can also take the pyruvate that was formed and again use it in gluconeogenesis. So that was our glucose-alanine cycle. So this cycle was just about the transport of ammonia in the body. Are these two cycles clear? Yes, okay, that's good. Good to know. Okay, lovely. Sorry. Now we have some clinical cases. And for this, you have metformin. And metformin is essentially a drug that we use in type 2 diabetes. And these are an inhibitor of gluconeogenesis, as well as some other reactions. It's essentially inhibiting anything that can lead to hyperglycemia. And this is used in type 2 diabetes. So it's inhibiting gluconeogenesis and glycogenolysis and so on. Biotin deficiency. Now, if you remember, there was in our ABCs essentially. Damn, this is gonna take. I'm so sorry. If we come back to our ABCs, biotin doesn't like raw egg whites and they find them stinky. And so that just means that when you consume raw egg whites, you have a substance in the raw egg whites called avidin. And avidin binds to biotin, and then this decreases the biotin concentration in your body, and this is causing a deficiency. So that's what this is. And this is a very rare scenario, but it can still happen. And then you have steroidal diabetes. So as we mentioned, what's it called? Cortisol, there was a star next to it. There's a synthetic cortisol, which is called cortisone, and also some other steroids. When you take these, because they are stimulators of gluconeogenesis, they're also causing hyperglycemia at some point, right? And this hyperglycemia can give you a type of diabetes. So this is about it for this part of the, what's it called, topics. I think we've covered pretty much all objectives, but we have to revise just a bit because there is something that we wanted to do, which was comparison of gluconeogenesis and glycolysis. So we'll just come to, we'll come to this, right? So again, for this reaction, we had glucokinase and we had hexokinase. And can anyone tell me what enzyme reversed this reaction? It's really silent in here. Okay, so to repeat the question, glucose is converted into glucose 6-phosphate via glucokinase or hexokinase. What is the enzyme that we used in gluconeogenesis to reverse this reaction? Glucose 6-phosphatase. Yes, really good. So we use glucose 6-phosphatase. Then we have another reaction where fructose 6-phosphate is converted into fructose 1,6-bisphosphate by PFK1, right? So what enzyme is reversing this reaction? Fructose 1,6-bisphosphatase. Yes, so F1,6-bisphosphatase. And again, the tase is very important. Please don't make the mistake of confusing the tase with tate, or 8, sorry. And then you go down, and then we have the final reaction, which is PEP converted into pyruvate, and this is done by pyruvate kinase. And so what two enzymes are the words used to reverse this reaction? PepCK, yes, that's one of them. Now, is this part 1 of the conversion or part 2 of the conversion in this whole thing? Part 2, lovely, yes, you are correct. And what about part 1? What's the enzyme that we use for part 1? If we want to remember, we can remember that the little brother loves Pepsi and he loves carbs. He loves pasta, bread, carbs. No answer. Okay, so there is no answer, so I'll just tell you again, it's pyruvate carboxylase. And to revise that, we'll go back to the slide, which was here. This is their little brother who loves Pepsi, and they love carbs, so they love Pepsi K, and they love pyruvate carboxylase. So the conversion of here, the conversion of pyruvate back to PEP is done in 2 parts. So first you have pyruvate carboxylase, which adds a CO2 group to pyruvate, so it's converting it from a 3-carbon molecule into a 4-carbon molecule. And it uses ABCs. And pyruvate carboxylase is an important enzyme, and you need to know it because it has so many things involved. It has the ABCs involved, it has acetyl-CoA involved, right? So you need to know it. And these two work together and they give you oxaloacetate. Then oxaloacetate, as you mentioned, reacts with Pepsi K and it gives you PEP. So is that clear? Okay, lovely. It says yes and another yes. Okay. Okay, another yes. Okay. So I would assume it is clear. So now, let's see. Is there anything else that I want to ask you? Now, I'm pretty much done with the lecture. This is pretty much all gluconeogenesis is. If there are any questions that anyone has, you can definitely ask me right now. So, yeah, I hope this benefits you. And yeah, if you have any questions, you can ask me right now. Okay, okay. Repeat gluconeogenesis. Okay, thank you. Okay, so one person is saying repeat gluconeogenesis. So, the whole process, I guess. Okay. Uh, if we need a quick summary of gluconeogenesis, we can do it here, I guess, right? I'll just revise gluconeogenesis quickly. So we have the reaction of glycolysis, and glycolysis needs to be reversed in order for gluconeogenesis to take place. So this is pyruvate to glucose, right? And so most of these reactions are reversible, but reactions 1, 3, and 10, these need a detour, a different pathway, because these are irreversible reactions. Recall that reaction 3 is the rate-limiting reaction. So for this reaction, reaction 10, we have 2 parts. We have pyruvate carboxylase, and you have Pepsi K. So these two, these convert pyruvate into PEP. And then you move on along the pathway of glycolysis, and you're just going in the reverse direction, and then you come to fructose 1,6-bisphosphate, right? And this reaction is reversed using fructose 1,6-bisphosphatase, and that is the father. Here you just had the brother and the granny at some point, and you have the aunt. So here you have the granny, here you have the aunt, here you have the father, and their father is leaving because what's it called? Because 1,6-bisphosphatase is doing the reversal of the reaction that the father of the father initially supported. And then we have the final reaction, which is a reversal of this entire thing. from glucose 6-phosphate into glucose, and this is done by the very sweet mother, which is glucose 6-phosphatase. So that sums up gluconeogenesis. I hope it's clear. Thank you for cooking with me, and if you can't, damn, my name doesn't show at all. I'll edit the slides and I'll give you my name more clearly and my number as well. But if you could scan the code, I would really appreciate it, like really, really appreciate it. So thank you, and I really hope this benefits you, and all the best. I guess we can stop the recording.